is Sara Willman, and welcome to Risk Management Professionals webinar series. Our producers, Kareen and Jasmine, will be in the background, keeping us operational and taking any questions. We're using a GoToWebinar interface to support our presentation. If you experience technical difficulties, please contact our office at 877-532-0806. We have staff available to help with troubleshooting. The image sizes for the presenter screen and PowerPoint presentation are adjustable. We also have a dialog box for questions. If you have any questions during the presentation, please submit them in the question box, and after the presentation, we will include them in our question and answer session. Sorry, we're having some technical difficulties. Is that better? Sounds good? Okay. All right, we're back. This webinar series is part of RMP's ongoing outreach program. RMP's core competencies and expertise reside in EPA RMP, OSHA PSM, CalARP, and SCMS program development, HAZOP LOPA studies, other hazard identification techniques, and a variety of other process safety and regulatory standards. So with that, welcome to my presentation on ammonia accidents, the importance of RMP PSM prevention elements in mitigating hazardous releases. I'll be covering a few famously investigated ammonia releases and discuss their correlation with RMP PSM prevention elements. Before I get started, you can see a little more detailed summary of our key services, which include process hazard analyses, process safety management, and CalARP programs. So today I will be describing 3 different ammonia releases and addressing their causes. It is most important to note what went wrong and how future occurrences can be prevented. Risk management is essential in mitigating hazardous releases and protecting the health and safety of company personnel and the public. I'll start with a recent famous accident at MILLARD Refrigeration that involved an evaporator coil failure and pipe burst, and discuss how detailed RMP PSM prevention elements could have helped mitigate the release. I'll continue to explain another scenario at a Goodyear tire and rubber plant in Houston that resulted in a tank overpressurization and explosion. And finally, I will close the presentation with an older incident at a cold storage facility that changed the way ammonia was understood in the industry forever. First incident I'm going to talk about occurred on August 23, 2010 at a MILLARD refrigeration facility, not far from a Deepwater Horizon oil spill cleanup site. A series of system characteristics and human factors led to hydraulic shock, which burst a 12-inch suction pipe on the roof and damaged the refrigeration system's evaporator coils. 32,000 pounds of ammonia were released during this incident, which traveled a quarter mile toward the oil cleanup site, putting over 100 off-site contractors at risk for ammonia exposure. The release occurred after a restart of the ammonia refrigeration system, following a 7-hour power outage. It lasted for a total of 4 hours, injuring 153 people, 36 of which required hospitalization, some in intensive care. The release was caused by hydraulic shock, which I'm sure many of you that work on these systems are well aware of. Hydraulic shock is a sudden localized spike in pressure when there's a rapid change in the velocity of a flowing liquid. This can occur within pipes, tanks, and especially at valve connections, and often happens when vapor and liquid are present together in a single line. Sudden changes in pressure and volume can cause catastrophic damage to piping and equipment. There are 3 types of hydraulic shock. Sudden liquid deceleration, also known as water hammer, is caused by the rapid closing of a valve. This causes a sudden pressure spike when the velocity stops so quickly and the liquid essentially slams into the valve, as you can see actually from this picture on the previous slide. Vapor-propelled liquid slug is caused by the entrainment of liquid on high-pressure vapor. Enough liquid will fill the pipe circumference to create a slug, which will eventually impart a large momentum on whatever obstruction it meets, which can be anything from a valve to an expensive piece of process equipment, like evaporator coils, for example. The 3rd type of hydraulic shock is condensation-induced shock. High-pressure liquid rapidly condenses in a line with both liquid and vapor, and as the vapor condenses, it undergoes a significant decrease in volume. This causes the liquid to accelerate and ultimately overpressurize the system. This type of hydraulic shock is most common, especially in low-temperature ammonia systems, and is associated with the transition from high temperatures and pressures to low temperatures and pressures. The MILLARD incident was caused by multiple factors. While troubleshooting issues during the power outage the previous day, an operator manually cleared an alarm, which resulted in an interruption of the defrost cycle in progress for a blast freezer evaporator. The evaporator switched directly from defrost mode to refrigeration mode without first bleeding the hot gas from the coil. Bleeding the hot gas is necessary to prevent a rapid reduction of pressure in the coil when the low temperature stop valve opens. The manual intervention reset the control system, so it did not recognize that the unit contained high-pressure hot gas before allowing the suction stop valve to open. Hot gas and low-temperature liquid mixed in the pipe, which caused the gas to quickly condense into a liquid, forming condensation-induced shock. The shocks ruptured the evaporator piping manifold and low-temperature suction piping on the roof. The problem went undetected because the defrost system is programmed not to allow liquid to enter the evaporator until the coil is depressurized. Therefore, if there were a problem, the operators would have been alerted. However, in this case, manual intervention caused a deviation from the normal sequence, overriding the system's normal programming. So here's a schematic that displays the configuration of the defrost system. Refrigeration involves sending the cold liquid feed through the coils via the liquid feed valve. During defrost mode, this valve, along with the suction stop valve, are closed, and hot gas is pumped through the system. In the case of this incident, the hot gas was never depressurized and remained in the coils upon startup. The liquid feed valve and suction stop valve were opened. Low temperature liquid was fed back into the system and condensation-induced shock occurred. RMP PSM prevention elements should be detailed and accurate and address all hazards that can lead to catastrophic incidents. One of the biggest contributions to this incident was the control system override that interrupted the defrost system. This is likely due to improper operator training of the system sequence and components. It is advisable to implement restricted access of major system controls so that only trained and authorized personnel can make changes to the system. This limits the risk of accidental system changes by operators who don't fully understand the system process or perhaps do not know what other controls are in place at the time that a change could interfere with. Another element at play in this scenario is process hazard analysis. The refrigeration system included multiple evaporator units connected to a single control valve group, which can be a severe overpressurization hazard. Initially, this design reduced costs by reducing the number of valves that needed to be installed. However, ultimately, the damage caused by the hydraulic shock was much more costly and impacted many lives. It is imperative that safety take priority during the design process and throughout the process life cycle. Accurate and thorough process hazard analyses can help mitigate hazards and bring to light weak points in the system. Efficient PHAs can allow for the design of better safety systems and independent protection layers. Also, it is recommended to design equipment to withstand unexpected system conditions, decreasing error margins and limiting the damaging effects of a failure. Regular inspection of equipment is also essential to keep equipment up to design codes and should be done frequently, especially after system shutdowns and before restarts. If an equipment walkdown had been done before the MILLARD refrigeration system was turned back on, the presence of hot gas would have been detected and could have been removed before starting. Therefore, a strong mechanical integrity program can significantly help prevent serious accidents. In addition, it is important to develop and follow safe and thorough operating procedures. Operating procedures should address normal process sequences as well as outline a plan of action to follow when unexpected or abnormal conditions occur. During the MILLARD release, the plant was not shut down upon detection of the release. Instead, the problem was located and isolated. This allowed the release to continue for longer than necessary. An emergency shutdown would have significantly limited the time and the amount of the release. Therefore, detailed startup and emergency procedures are necessary and personnel should be trained accordingly. The next incident I'm going to cover is an accident that occurred on June 11, 2008 at a Goodyear tire company. A heat exchanger ruptured and tragically killed an employee and injured 6 others. Pressurized anhydrous ammonia was used in the heat exchanger to cool chemicals used to make synthetic rubber. The day before the incident, operators closed an isolation valve located between the heat exchanger shell and the relief valve in order to replace a burst rupture disc. The rupture disc was successfully replaced, but the isolation valve was never reopened. On the day of the incident, another operator closed the block valve that isolated the ammonia pressure control valve from the heat exchanger. He proceeded to connect a steam line to the process for cleaning. However, since the block valve and the isolation valve were now both closed, the flow of steam had nowhere to escape. Pressure could not be safely vented, and the heat exchanger ultimately ruptured. Flying debris killed one employee walking nearby instantly, and 6 others were exposed to the ammonia release. The plant was evacuated. Fortunately, the employee tracking system also failed to account for all workers, so everyone assumed the plant had been fully evacuated. The body of the killed employee was not found until several hours after the plant operations had resumed. Here's a diagram of the heat exchanger. The ammonia flows through the exchanger shell, acting as a coolant for the hot rubber components in the tubes. The ammonia flows in from the cooling system, exits back to the cooling system before returning and continuing the cycle. On the day before the incident, the isolation valve at the top of the exchanger was closed, cutting the relief valve off from the system. The next day, the block valves on the ammonia vapor exit line were closed. The exchanger easily overpressurized with the continuous addition of steam to the closed tank. So many factors play into the occurrence and severity of this incident. The 2 key prevention program elements to take note of are emergency planning and response and maintenance. First, plant-wide alarm systems were unreliable, and alarm pull boxes were out of reach due to the ammonia release. And also the computerized employee tracking system malfunctioned, delaying supervisors from immediately retrieving a list of personnel in their areas. As a result, handwritten employee and contractor lists were generated based on the workers congregated at safety points. Not all supervisory and security employees were familiar with the employee accountability procedures. It is important to maintain thorough and efficient emergency procedures for a facility and ensure that all employees are properly trained on their implementation. Evacuation and shelter-in-place drills should be done every so often, and workers should have easy access to emergency routes and procedures. In addition, a quality process hazard analysis could have potentially addressed the faulty alarm issue, and that problem could have been remedied long before the incident. The other key prevention program element to address is maintenance. This accident was caused by a miscommunication between operators and a lack of proper maintenance documentation and checklists. Lockout-tagout procedures were not followed, and no required maintenance authorization signatures for the start or completion of the maintenance were obtained. ASME Boiler and Vessel Code, Section 8, requires that when a pressure relief device is temporarily blocked and there's a possibility of vessel pressurization above the design limit, a worker capable of releasing the pressure must continuously monitor the vessel. It is important to comprehensively train employees to follow outlined maintenance procedures and pay very close attention to any maintenance operations being conducted. Employees should constantly communicate with each other and document all maintenance activities to ensure no inadvertent actions are conducted on pressure vessels. It could take just one component accidentally left out of place to cause a disaster. Systems should also always be checked after maintenance is completed to make sure everything is in safe working order before introducing any new conditions to the system. And just to clarify, maintenance and mechanical integrity are essentially the same thing. It's just that maintenance is a Program 2 prevention element requirement, and mechanical integrity is for Program 3. Lastly, I'm going to quickly cover one more example that occurred about 30 years ago and changed the way that ammonia safety was regarded from then on. An ammonia explosion occurred at a cold storage facility in Shreveport, Louisiana that claimed the life of one responder and significantly injured another. There was a leak in one of the small freezers, so responders used information available in the National Institute for Occupational Safety and Health manual to determine the proper PPE, including self-breathing apparatuses and suits. The goal was to get close enough to work on the leak. Unfortunately, what was not known is that ammonia can ignite at certain concentrations and reacts with certain metals and acids. However, it was classified as a non-flammable gas. Steam was sprayed into the space, a common tactic used to ventilate smoke, but water reacts with ammonia to create a white cloud. So the responders entered the cloud with a man basket-equipped electric forklift in order to reach the location of the leak. Unbeknownst to the responders, the forklift had sulfuric acid in the battery and silver contacts that emit a blue spark upon opening and closing. The ammonia quickly ignited. This incident, among others, influenced ammonia safety standards and documentation and allows us to now have a much better understanding of the chemical's hazards. Regarding RMP PSM, the process safety information prevention element is particularly important to ensure all dangers associated with chemicals and process elements used in the system are properly documented and hazards are addressed. If more accurate safety information had been obtainable by the responders, the tragedy could have been avoided. Employees and responders should be fully trained on the dangers of the chemicals they are working on and know how to respond to them in an emergency. Important lessons to take away from this accident are to never enter a visible cloud of ammonia, measure the concentration when responding, and carefully control any potential ignition sources at your facility. Here are a few references, mainly Chemical Safety Board information for the case studies and some of the ASME codes. We also have a few webinars coming up that you may be interested in. The CalARP Program 4 and OSHA 5189.1 updates will be coming up soon. Not long after that, we'll be continuing with Part 5 of our IAR standards and how they apply to RAGAGEP. And then we'll be talking about some common causes in HAZOP applications. In addition, we will be in attendance at the RETA conference in Hershey, Pennsylvania on September 26th and 29th. So I hope that we will see some of you there. The audio and PowerPoint presentation are being recorded and will be available for viewing in about a week. With that, are there any questions?
Yeah, we have some questions. The first is, how would you recommend improving communication between employees to prevent potential incidents?
Well, first off, written documentation is actually a very important part of communication, especially in our industry. But a stack of papers isn't very useful unless people read it and are trained to look at it. So essentially, you want to ensure that operating, maintenance, and emergency procedures are written very clearly and effectively. You want an operator to be able to look at a piece of paper and see a stepwise, operating procedures and know exactly what to do and be able to understand it. So importantly, you want to be able to train your employees on the entirety of the program and emphasize adherence to all procedures and make sure that the training is effective. Include quizzes, demonstrations, have the operators practice. Per RMP PSM requirements, employees are to be trained on the program upon initial hire and have refresher training every 3 years. Operating, maintenance, and emergency procedures should be reviewed annually or more often if deemed necessary. And specifically for emergency planning, drills like evacuation, shelter in place, earthquake should be performed at least once a year as well. And with that, your employees will learn to communicate better as long as they practice doing the procedures.
And then someone wanted you to quickly repeat the difference between maintenance and mechanical integrity.
Okay, so maintenance and mechanical integrity are very similar. Essentially, maintenance is a Program 2 requirement, and that's what they call it, and mechanical integrity is the Program 3 requirement. But they essentially contain the same elements.
Okay, and then what should be included in an effective maintenance program?
Perfect. So detailed maintenance procedures, first of all, would want to be included. That would include the maintenance and inspection frequencies on all pieces of equipment and also the types of tests that should be performed. These can be provided via manufacturer's recommendations or international codes. You typically will want to follow recognized and generally accepted good engineering practices, also known as RAGAGEP. You can use standard codes for those for the design and the maintenance, like ASME or IAR. For example, you might want to use maintenance checklists according to RAGAGEP and document all training documentation for all employees and contractors. And also maintain a history of all the work performed on equipment by employees or contractors. As we saw with the Goodyear tire incident, that was caused by a lack of checklists. There were no authorization signatures. No one knew whether the maintenance was happening or not. So that's why it's really important to keep everything documented, and you definitely want a history of what's been going on in the facility.
Okay. Next question is, could you discuss any alternatives to ammonia as a refrigerant?
There are a lot. There are some. Ammonia is typically the best for the environment, which is one of the main reasons that it's used. I'm going to have to do a little bit of research to find out any specific chemicals. I actually don't know that off the top of my head. So if you provide me with your email, I will be able to look that up for you right away and get back to you.
Okay, and this one's a little long. With the MILLARD incident, how common is it for the manual intervention in the defrost cycle? Was this an unusual circumstance? Can you repeat how the several evaporators connected to the same control system contributed to the incident?
Okay, I'm going to go back a little bit. Do that. Let's see. So what was that? Here we go. Okay, so what was the first half of the question again?
With the MILLARD incident, how common is it for the manual intervention in the defrost cycle?
Okay. So I don't imagine that's that common. This was an unusual circumstance because they had a power outage and it happened during the defrost cycle. So I can't imagine that that happens too often. As far as the evaporators all being connected, that was kind of an issue because you essentially have all of these evaporators connected to one valve system. So if something goes wrong, it's a lot easier for them to overpressure since there's so much ammonia going through this one valve system. So it's often recommended to put your evaporators on different valve manifolds so that you have less ammonia. So for example, this was caused by a hydraulic shock incident, which means there was a lot of ammonia going through these, and since there was all these evaporators, they all, one of them blew up, and it caused all of this ammonia to shock the system. If there'd been, less um, less evaporators on the one valve, perhaps it wouldn't have been as serious of an issue. It may not, maybe it wouldn't have ruptured. Perhaps if it did, it would have been a less severe leak.
And going off of that, does IIAR permit several evaporators connected together? Was this a design issue to current standards?
It may be. I'm not totally sure about that. I'd have to look through. It might be. I I don't. I'll have to look at the IIR standards. Again, prevent me with your email, and I'll be able to answer that for you.
Okay, it looks like that was all of the questions.
Okay, great. Thank you all so much for attending.